Okay, we're here today at the Morton Arboretum with Dr. Gerould Wilhelm. And he's one of the members and leaders of the Conservation Research Institute, which does research in conservation. He's also a research position at the Morton Arboretum where we're at. He's a long-standing botanist, and he's the author of the Flora of Chicago region, the next version. He earlier with Swink and Wilhelm, and now it's Wilhelm, and I don't know the other lady.
Laura Rika.
Yeah, right.
She really knows the plants certainly as well as I do, plus insects.
Insects, right. There's a whole insect component to this. And the main purpose of being here today, as I turn this over to Jerry, is to go into the Floristic Quality Index. Our users do a lot of mitigation, restoration with wetlands, and this is a method that's used in a lot of parts of the eastern U.S. and Midwest, and how that could be useful in measuring the pre-existing on that site, not historically, but the preconditions, the mitigation, a restoration, and a response to certain types of treatments for the plants. And so that'll be a big thrust today, and it's very important for our users. It's used actually a lot in the mitigation programs, and I thought we'd come here and sort of pick your brains as to how you came up with this, what it is, how it works, and maybe you could even go back and 30 years ago when I was here, you explained to me how you measured a prairie with burning and saw different responses, and at least give us an example of an application for those folks. So,
well, the beginning, before we had that method, which I sort of came up with in 1975, 76 area, when I was starting to, people were trying to, this after the National Environmental Policy Act, so we've been in it 5 years already. People were wanting to save woodlands, they were wanting to save prairies, and they would go before plan commissions or city councils and say, we really need to get the county to buy this land because it's a very high quality piece of land. And people would say, and the plan commissioners and or city board members, city council members were usually not trained in the environmental sciences, much less botany. And so it became, after a while, everybody was coming in with, if they had a wood lot, and saying it's a very nice wood, we need to save it. And so we needed some way to help the policymakers understand the importance of saving a particular area and regarding it valuable to the to the community. And so we recognized that all plants, all the native plants, as you come to know them, they tell you only sort of true things about a place. Now, the plants are not ego-driven, tenure-tracked, governed by doctrine. They simply tell you only truths about what you're seeing. They will languish if we're treating them well, or treating them poorly, or they'll prosper and flourish if we aren't. If we are treating them well. And so we gave every plant in the flora, every native plant, what we call a coefficient of conservatism, which is basically a level of confidence that the plant tells us whether we're in a remnant situation that the impact upon which would be irreversible or irretrievable if impacted, or would not. So, for example, the poor man's pepper, Lepidium virginicum, if somebody brought one into the herbarium here and say, how confident are you I was in a very high quality prairie, I would say I have no confidence. You would probably pick that up in a crack outside in the parking lot. Okay, so that's a 0. On the other hand, if you brought in the yellow lady slipper and said, how confident are you I was in a very high quality wet mesic prairie, I'd say I'm 100% confident you were in a high quality wet mesic prairie, and I'm not sure of it, so that would be a 10. On the other hand, if you brought in the little red Trillium recurvatum, and said, how confident are you that I was in a woodland when I collected this, I would say, I would bet you I am 95% confident, maybe more confident than that, that you were in some kind of original soil that was once wooded. However, I couldn't tell you how degraded that system was, how much abuse it had taken, because it can take a lot, but it only grows where it's always grown, under remnant conditions. So that would be a 5. And so the 5 is kind of this pivot point. And if you, on the other hand, if you brought in something like the evening primrose, by Ennis, and said, how confident are you I was in a remnant when I collected this, I'd say, unlikely. More than likely, it probably wasn't necessarily right in your dooryard, but I would give it maybe about a 20% confidence that you were in some kind of field, not original soil. Maybe that's a 2, you see. And so your spectrum runs in, and those really disturbed areas, which are not remnant, from say 0 to 5 or 0 to 4. On the other hand, if you brought in a Carex hiscockyiana from somewhere and say, wow, you were in a pretty nice woods, and not just some woods that had been degraded, but a woods that maybe taken some abuse, but it was pretty high quality woods, that would be like an 8 or 7. So the spectrum runs that way through every plant, and when you have all the plants in front of you, just like the wetland categories were initially organized around 11 coefficients, so was or 11 categories, so was the C value. And then when you apply these and you go to an area like say a barnyard, and you start recording the native plants in there, nearly all of them are going to be 0s. Or a lawn, if there's any native plants in, they're going to be 0s. And so you're going to take the average of all the plants you find, and that tells you what the average mean C is, or the mean C, what we call the mean coefficient of conservatism. So if it's a 0, it means you're in absolutely 100% confidence, not a remnant. If you go into a place, however, and get a mean C value around 4, in order to get to a 4, you have to, because there's always a number of 2s and 3s and 1s out there, you must have some that are in the 6s and 7s. So a mean C of 4 means you are in some kind of remnant. It could be pretty degraded. On the other hand, but if you had a mean C of 5, that's a very high quality area, because every place has the scar tissue plants, have those plants that respond to disturbance, so every place has 0s, 1s, and 2s, but not every place has 8s, 9s, and 10s. And so if you have the full array, you're going to have a mean right in the 5s somewhere. That's high quality, very high quality. Now, it does require the downside of the whole program is you have to know plants. I'm afraid that's just, but we require people who design bridges to know math. And so there's nothing particularly outlandish to me, nor do I particularly apologize for requiring people who are trying to understand the landscape to know plants. Maybe that's just as a botanist speaking, but why should understanding the earth require less training and less application of effort than engineering? And nevertheless, if you know some plants or many plants, if you go into an area, say an old field, and the old field has 100 species in it, and you can only identify 15 or 20, very quickly that mean C starts to express itself. You see, so if you go in and identify 20 plants of the 100, the mean C might come, let's say it comes out of 2.5. You can find another 20 plants, maybe it might come out 2.6, something like that, 2.4. But if you quickly are able to gauge a metric that gives you some idea as to where you're standing.
So do you feel there's any difference in the numerical outcome rating if you looked at abundance?
No, because abundance would be a very difficult thing to develop a metric for, because it changes throughout the season. It changes, for example, a plant that might seem abundant and even robust in spring is hard to see in fall.
Okay.
And also, since every place is unique, you don't know what the abundance means. So, for example, there may be I've seen it over and over in my life, a prairie along a railroad, for example. There might be a patch that has a lot of Hypoxis hirsuta, the little yellow stargrass that we give a 10, but it isn't everywhere. But that doesn't mean the high quality prairie where it isn't high quality too. And so also, if you went back there in August, you wouldn't see it. So the abundance is a very difficult thing to other than, unless you're looking at endangered species or has some other program you were working on, it has little relevance to evaluating whether you're confident you're in a remnant or not.
Right. So it's a presence absence.
Presence or absence.
With
it speaks well enough for that purpose.
What a rating that gives you your C value.
Well, it gives you the mean C. If the question is, how confident am I that where I am is a remnant? Okay. And what's the quality? If you have other questions, you need other techniques. Mm-hmm. Okay? But remember, with respect to abundant, if you go out with it and do a transect and take all the species in a quadrat, in a prairie, say, here we are in the Midwest where we have a lot of prairies, in a quarter square meter, there are 15, 20, even 25 species there. If you ran the coefficient of similarity of quadrats just 5 paces apart in a prairie that would all be called, say, wet mesic prairie or mesic prairie, and looks sort of the same, the average coefficient of similarity, 2C over A plus B, where C is the number of species in common, and the species in A and species in B is at the most 70%. So every square meter of remnant land on the globe is unique to all others. And so so how would you develop a theory as to what the commonness of any one species was in that quadrat at that time of year, at that moment, or that year even?
Right.
And so it doesn't, if you're doing some kind of ordination or plant community descriptive type work, you may bring in some other tools.
Right.
But the question that the C value is answering is, how confident am I that I'm in a remnant? And the reason that's important is that remnants cannot be replaced. They are unmitigable. So that, for example, since the middle 70s, particularly since the middle 80s, when the Section 404 of the Clean Water Act was really first applied here in the Chicago region, right here along the north-south tollway, and we began in a serious way mitigation projects and trying to restore wetlands and plant communities. That was beginning already about 1984 or 85, I would say. John Rogner was the chief of the regulatory functions branch at the Chicago District Office and really brought that to the foreground, in my opinion, here in Chicago. I'm not sure how the timeline goes elsewhere, but it took a while after the Clean Water Act of 1972 to begin to respond to some of the requirements in there, or implied requirements. By the way, the Clean Water Act, in its preamble, said that the idea was that all waters of the United States, this is in 1972, will be fishable and swimmable by 1984, which mark we missed.
Yeah, by a few years.
By a few years. But so, of all the restorations that I would regard, that were regarded widely as successful, the average mean C as an inventory level is 3.2 plus or minus 0.7, which means that you're 95% confident that when you get to the end of your project after 8 or 9 years, you will not have achieved natural area quality. If you look at the quadrat levels, the average mean C per quadrat, remember they're all different, it's actually because the distribution in most restorations isn't like a higher quality plants aren't necessarily widely distributed. The mean C drops from 3.2 to 2.8 per quadrat, plus or minus 0.9. And so even after 8 years, and even after pretty good burning, the distribution of higher quality or higher plants with higher C values is still weak. Right. And so generally, if you're trying to project that over maybe say 50 years of burning, in that area where you've recruited and held enough species to have a mean C of 3.2, it might take that many years to get the actual quadrat level mean C up to that. But that would be the trajectory you'd look for to see to what extent you were actually improving, your system over time. But the important thing is, if you go out to an area, even if an ecologist or someone working for the heritage program would say, well, that's not really that great of woods, that's not really that great of prairie. If it has a mean C in the 4s, it might be the kind of thing that people like that would eschew and turn up their nose at because it's not perfect. But the fact is, it's still unmitigable. You can't replace it if you wreck it. Mm-hmm. And so if you're going back to the National Environmental Policy Act, where the Congress had in mind that we were to examine the degree to which the impact on our area was irreversible or irretrievable, you must conclude that any area that's mean C in the 4s is in that category.
Right.
So now that doesn't mean you certainly, we shouldn't have a law necessarily saying you can't do it, but all people in the culture and in the array of policymakers and people coming to make a decision on that land, you have to know that for generations here on out, we will deprive them of the quality of this site and what it can teach us about how we interact with that land and how to manage it. Right. So it really, when you lose a remnant, you really have lost something irreplaceable. Right. Related to abundance is species richness.
Yes.
And the index, the Floristic Quality Index, includes richness. And so, for example, the way we handle richness in evaluating whether a place is remnant is quality is we take the species richness and we take the square root of it and we multiply that by the mean C, and that helps separate large sites of similar quality to very small sites, or helps move small sites that have very high quality but low species richness up against a very high site, very large site with lower quality. And so they can stand with each other that way, and that's why we do that. We could have taken the natural log of the mean C, but it just wouldn't spread much. So just to make it more visual, more easily comprehensible, we just took the square root.
Right.
And we were there. What we were trying to do was accommodate the species area curve. Right. So acknowledging that the more technically, the more space you have, the more species richness you'll have. That doesn't really apply well because you can have in a small prairie, say a third of an acre, a very high richness, and then you get to the edge of it and expand the place out another square mile and have nothing. So area in and of itself doesn't mean anything, but if area does mean something, then the species richness would account for it.
Okay.
You see?
Yeah.
And so that's the purpose of it.
I actually had that question 30 years ago. Why are you square rooting species?
Well, it's just to regress it in the same way that
And I asked a mathematician / engineer, why is he square rooting this? Mm-hmm. And he gave me a math answer that made no sense. Because
it could have taken the natural log. You get the same function, but it just wouldn't be as the tool wouldn't be. But you use like a very small nail,
right? Right.
So you use a big nail so you can see it.
Yeah, exactly. It just magnified it, the differences.
So in a restoration, what you'll get if you get a mean C up in the 3s, you will have about. You could have as many as 8, even 10 species per quarter meter square. Mostly it's around 7 or 6 or even less. And so if you had a mean C, say, of 3, and you had 9 species, that would give you an index of 9. Mm-hmm. Okay, so that gives you an idea. Yeah. And so that, generally speaking, as your restoration matures, that sort of beta level richness will also increase and your index will also rise, even if the mean doesn't necessarily continue to rise.
Right. The diversity starts.
The diversity can start to rise, particularly if you're burning and you're once you start to heal the soil and become stable, and you're burning at a good burning regime and just a well-funded management approach, you can start spending money on enhancement seeding after about maybe 10 years.
Right.
Start putting in some of those seeds, and maybe 10 years after that, something will happen.
Right.
You start to notice things. Mm-hmm. But by way of contrast, so that would be a pretty good restoration of a mean C of 3 and 9 species. That's a 9, right? If you had in a high quality remnant, you could have 25 species per quarter meter square with a mean in the 5s, or even 6. So 5 times 6 is 30 in a quarter square meter,
right.
You see? And so that's very possible in a high quality remnant.
Wow.
So compare that quarter meter square to a remnant versus a restoration. 25 to 30 versus a 9, which is already pretty good. And so you just can't get there.
Right.
You see, we don't have in order to get species richness up in a restoration, you also have to the soil has to begin to accommodate insects that pollinate.
Mm-hmm.
And in order to accommodate those, the soil has to get better, and they have to be somewhere around.
Right.
A lot of those insects are, while we think of them as vagile, they're not as vagile as you might think.
Right. Right.
And so some bees, for example, Laura will say, will live in the same square meter year after year. They don't go anywhere.
Huh. Huh. Now, do you think that's a universal, quote unquote, I don't want to call it a rule, but a pattern across the landscape? Let's just call it North America.
Across much of North America, where there's a serious discontinuity of what I've been talking about, is when you get into the tidal zones, because tidal wetlands are governed by the mathematical ebb and flow of tide, and there aren't many plants that can accommodate that brackish water. Mm-hmm. And so the tidal wetlands are a whole different theory of thought, whereas the wetlands of the Great Lakes, the movement, first of all, the movement of water historically wasn't very much.
Right.
And secondly, if it did move, it was cold and clean, and you didn't have that mathematical ebb and flow of tides and the lunar cycle. You had just this constant rate of discharge. And so the way you think about the hydrology of the two wetlands types is quite different.
Yeah.
But I just wanted to talk about where abundance isn't important. The species richness is important in terms of helping you. If the question is still, how well am I tracking on my restoration or my rehabilitation of a remnant even? Right. So we also use it to test how well we're doing in rehabilitating a remnant. Mm-hmm. If we go out here, I'll show you later the Schulenburg Prairie, and that's actually a restoration, de novo restoration, with mean Cs in the 5s. Wow. And it has 12 to 15 species per quarter meter square. Oh. Not plants, species.
Wow. Yeah.
And that's because it's been burning every year since 1967, and he's even getting bees back. Huh. So that's something that's on its way. But most prairies, either they don't burn every year or some don't burn at all, some restorations. But in the Midwest, you have to burn. If you're not going to burn, you might as well not put any money in on it. Yeah. I would say, however, that even if all you had, frankly, at the beginning of a project, if you just put back tall grass, not even any rudbeckia or flowers, just tall grass, and get it going and burning it, that alone would begin to have an impact on local hydrology, on flooding. It would begin to repair the soil, and in the long run would become an asset.
Wow. Huh.
And so just the planting of tall grass would be huge, which was like say even planting CRP is a big thing.
Yeah, right.
The study Purdue did, and they were measuring sometimes a ton of a net accrual of organic carbon per acre per year. And just some of that was just not that maybe even the best grass.
Right.
But perennial.
Yes. What do you think the vectors? Let's say you have a 3 or a 3.5. What or a 2.5? What are influencing it in a wetland that holds it back from in 10-year time period not having a higher C value?
Well, I think
there are general patterns.
Oh yeah, there are general patterns. The historically, because the landscape, the overall broad Midwestern landscape was a perennial landscape, a lot of soil organic matter in the soil, virtually, if you get 37 inches of rain a year, 37 inches is about 1 million gallons per acre per year that would fall on the ground. It would all go in the ground. And then in the Trans-So's Prairie Peninsula, this area where we are now, about that much evaporated. If you put an evaporating pan out in your driveway at the beginning of the year, it'll have the same amount at the end of the year as it did at the beginning of the year. And so, but the wetlands, the wet soils were, the wetlands did not receive, they received all their umbrotrophic rain, and they evaporated that. But where they got their surcharge water to make them wetter than upland was that the rain that would go in the upland would, following Darcy's law, basically follow a straight line from the boundary it went in to the boundary of the wetland, and that's where the water would come out then, having gone through the zone where the average temperature is the average daily, where the temperature is the average daily temperature constantly. The water would come out at a constant rate of discharge, a constant chemistry, and a constant rate. And that's why the Midwestern wetlands, and which were they were all discharge wetlands, there were no flow through, unless you want to consider the Illinois River a flow through wetland, which received most of its water from the Kankakee, the Fox, and the Sangamon and other rivers that came in, but its slope, its head loss from Hennepin to Alpin, over 200 miles, was an inch per mile. So basically a long lake. In fact, the French sometimes call it the Lac du Illinois, and it confused it with the Lake Michigan, you see, because it was this big lake. Yeah. That had negligible discharge of the Mississippi, rarely ever flooded except during a spring snow melt with the heavy rain. And so these were, so all of the wetlands, particularly in the wetlands in the Midwest, were tended to be, particularly the fens, the seeps, and things like that, were always associated with outwash. And so the rain would go in the outwash, usually shoulders along streams or in wherever you had glacial outwash, and work its way down and come out into a fen or a seep or a spring. The prairies, the wet prairies, were generally or derived from silty clay loams, and they were, depending on their situation, positioned such that they would actually, they didn't seep. They just sort of stayed wet, and were up from maybe a little bit. There may have been some gradual seepage, but largely the mollisols were pretty wet historically. When Sampson did his study of the prairies of Illinois in the 1920s, he said that the limiting factor for prairies in general in Illinois was the wetness of the soil, because those mollisols, by the physical chemistry of the mollisols are actually hydric, but they were left out of the most core list because it would interrupt too much agriculture, because so much agriculture was built on mollisols, which were dewatered and drained and this sort of thing. So their very nature, because they have so much organic matter, for example, on the prairie, the tall grass prairie had the average, they had about 15 to 18,000 kilograms of root mass per hectare, as compared with corn, which has 800, or bean about 300. Wow. And so you had that much soil organic matter, and those root systems turned over completely every 3 years. So all that organic matter, just like in a worm composter, is making tea at the bottom. All that organic matter is constantly making tea, water. You see, and so the soils, and plus the bunch grasses, which they were all mostly bunch grasses. If you've ever been out in a prairie or even a brome field on a July day at noon or at 10 o'clock in the morning, you'll be wet to the thighs because of all the dew that comes in the night on those plants. Well, if you burn that prairie on a regular basis, those sleeves are standing pretty much straight up, and that dew can go right down into the ground. If you don't burn it, right, then you have lying down duff from the year before, or the snow packing it. When the dew comes, it sits on that duff and dries out. It doesn't go in. So just not burning the prairie can help dewater it.
Well, so what you're saying then is, so if you have a 2, 5, or a 3, you're probably not going to get to the 4 or 5 level because all the other adjacent or upland aspects that are feeding the water in have been disturbed. So it's a bigger picture than just the wetland, the species, and those, however it's been designed. You're lacking the nature, so to speak, of the adjacent.
You're lacking the essence of a Midwestern wetland, which is groundwater discharge.
Right.
And so what's happened instead is we have taken the source of water for our wetlands, and by paving over or tilling over the source of that water, we have changed the quality of the water that goes into the wetlands. Now it's mostly surface water, and surface water is hot. It comes in the growing season, not cold, icy water from the late spring or winter. And so you have now, for the first time in the history of the earth, hot, dirty water flowing into areas where we once had about half our flora of our 1,800 species, half the wetland plants. Half of our flora is basically disenfranchised because they require cool, clean discharge water. And so what tends to happen instead, the more you actually, if you flood an area once every 2 years with modern stormwater runoff along a river, no matter how much you spend putting into a wetland restoration, you're going to wind up with weed canary grass, and now more and more Phragmites and this sort of thing. And so the reality is, when you change the habitat, you change the inhabitants. And one of the difficulties with a lot of aquatic insects, a lot of aquatic plants, is essentially ectothermic. And so they were historically, all their evolution was their metabolism responded to and worked at the rate at which the water gradually warmed in the season and gradually cooled and then into the dormant season. Now we suddenly change the temperature on these guys and start flooding in this warm water that nestles in, and the plants are ectothermic. And so the root system is ectothermic, and so when we put that much warm water into our systems, the whole system basically collapses. It'd be like if you suddenly had a temperature of 108, or it's going to feel good. So
you've taken what historically would have been quote unquote a higher quality flora location, and by changing the water temperature and the soil conditions, you've narrowed down to a much narrower, you've changed all the chemistry and the water temperature, eliminating any potential for it to ever come back at a higher level.
Because nothing's evolved to that except, and weed canary grass isn't even native except further north, and that's a different variant, but we've changed it. And so it's unreasonable to think that we can build a wetland that is evocative of an aboriginal wetland. The other thing to remember too is that if you just 1 gallon per minute coming out of a rill in a seep or a spring, 1 gallon per minute is 520,000 gallons a year. If it stays going, which they would do in a natural system, that's half the annual rainfall on 1 acre. So you have to imagine what kind of quality landscape in the upland that we're not charged from a regulatory standpoint to be attentive to, that maintains that flow of water. So many of our springs are still be drying up because we saved the wetland but wrecked the upland.
Right.
And in reality, there really is no such thing as an upland or a lowland. It all gets the same rain, and they just interact with each other in different ways.
Right.
And so our regulatory emphasis has been on wetlands because we started coming at it from the Clean Water Act.
Right.
And so that has been the sort of epistemological evolution of our thinking. I personally think we need to reevaluate that a little bit, and if we're to have any fish left and to have anything left at all, to have any vitality left of the earth.
Right.
The other thing about it, when you've lost the ability for the water to go in, that means that the rainwater which is coming down goes off, which means when you don't get rain, you have drought. Well, there was no drought east of the 100th meridian. prior to, even at the beginning. So that's what was important about the 100th meridian, was that you never needed to irrigate. You see, but now we need to irrigate to beat hell, because we've depleted the soil organic matter in the soils,
Right.
and so the water goes off, and now people who are commodity scale in agriculture and don't put organic matter in think that we call a drought. But it's an artificial situation, and the flooding is artificial. And so we never used to have the floods because the water would go in, not off.
Right, right.
And so in fact, Amos Sawyer published an article in the Transactions of the St. Louis Philosophical Society in 1874, and the title of the article was "The Reasons for Climate Change in Illinois." And no one argued that the climate had changed, because he had lived in it. I saw it change in Florida when I was there. But every afternoon, he said, the warm air would rise, and it would get the cool, and you would get a rain shower. He said when we started, okay, so step back for a minute. We're getting a little off C value, but it relates. But after the War of 1812, the federal government started giving patents to veterans to farm land in the Jeffersonian way, because that was civilized, do agriculture, giving a veteran about 80 acres of land in the Midwest, Illinois and whatnot. And the problem was that so much of that was too wet to plow. And at the same time, in that age, in 1815, say, 1818, Illinois became a state, the doctrine of contagion throughout the world was that a disease arose from ill humors in the wetlands and whatnot. And so the federal government thought you could have a win-win situation, because you could drain the wetlands and give every farmer an equal opportunity to farm 80 acres. Win-win. Well, Amos Sawyer noted that, of course, we now know about contagion. It doesn't have much to do with wetlands other than mosquitoes. But Amos Sawyer noted that with the ditching, there weren't any tiling at the time, that the ditching of the prairies and the draining of the prairies, there was less water in the land to rise up and cause a rain shower, and the rain was becoming far more stochastic in its occurrence and far more violent. And so he was noting this in 1874, and he attributed what he called the aqueous agents. It's an interesting paper. We quote some of it if you go to our website, Conservation Research Institute, and check out a paper called The Ecology and Culture of Water that Jim Patchett and I wrote. We referred to a lot of that and quote some of his conclusions. But the fact is, the way water is in the soil, and I think of the soil as what I call that sort of sweet interface between heaven and earth, where life is. And that soil, when it's healthy, has a connection with the thermal mass of the earth below. And so that all of the ectothermic organisms, the bees, the wasps, and all the things that make their homes in the soil, the plant roots, all these things, the soil temperature cannot change except very slowly. And so ectotherms can handle that. Then in the winter, it comes back again slowly, gets cooler again. It's actually not the way you think about it. It's a little offset, the curve, but the temperature didn't change fast. And so, but when we have tilled out through our commodity scale agriculture, we can't put organic matter back in, we have now changed that relationship as well. So that so much of the soil that sits out there through much of the summer, after with only 90-day corn or 90-day bean, it sits there and it cooks. And Laura and I, my co-author on that book, have registered, and some soils have been disturbed where we're collecting ants, temperatures on a September day where in a sward of little blue stem grass, the temperature would be 85 degrees on a 72 degree September day, 115 degrees out just where the soils were disturbed. And the only ant that can even survive it by running across it is Forelius bruinosus. And very few things can live in that. And so we've created a situation where throughout a lot of the growing season, the soil is simply changing temperature too fast, getting too hot, outside the evolutionary patterns for most organisms. And so getting back, if you're expecting one thing you can test if you're doing with wetland mitigation, or if you're proposing to mitigate, it seems to me the first question you need to ask is it mitigable? This land that we've evaluated, if it has a mean sea in the fours, you should tell the policymakers and the people who make the decision and the people who are trying to make a buck off that land that the culture needs to know, the people need to know, that if we wreck this, we can't replace it. On the other hand, if you were to take an area that had a mean sea, say in the twos or low threes, you can probably restore that if you're not going to put stormwater in it. If you're going to put stormwater in it, you can't do that. Right. But so there is up on the terraces, or if in the development, if you have access to sort of re-inhabiting, if you will, re-relating to the little watershedlet that gets your water, it's possible through upland design, architectural design, landscape architectural design, and engineering to make water go back in the ground and come to that area in a better way. Right. And you can actually then begin the process of producing something that can have some biodiversity and have a long-term chance of becoming something other than just a canary grass.
I was going to ask you, given all these limitations which go beyond the wetland boundary, and you're just mentioning how you could engineer for it, what would you, let's say you had a 2.5 rating, what would, and over some period of time it improved, what would you consider, well, it's not going to go to a 4 or 5, but what would you consider successful, or it's as good as it's going to get and it's not that bad? Could you put that into?
Well, a couple of things. In a wet prairie situation, say, in my mind, if you can get up into the threes, what's going on as well is over the very long term, probably not in my lifetime, but over time, that root mass of those tall grasses is starting to rebuild the soil. And if we do enough of this and engage that kind of landscape in the upland, by degrees, and you burn it every year, it can slowly, by degrees, get better. It could probably move into the fours if there's enough biodiversity around. One of the issues, however, is that of our 450 bees, for example, only about 30 will visit an artificial garden. So most of our bees are confined to remnants. And we have at the Schulenburg Prairie out here, which has been in since 1967 and been burning every year. By now, even though it's hard to see much change in the soil, we know it's happening a little bit, but it might be hard to put a metric on it, on pedon development. Maybe you could look at in a more detailed way. But we've actually picked up some conservative bees, Coletes estavelas, Coletes kincaidii, and a few others that are my co-author has found out there, that suggest that over a long period of time, with annual fire and improving soil, it could begin to approximate something real again, and something beautiful, and something that would begin to hold the rain. I actually think that we need to think as well about the Germans have an interesting approach to water. In America, we have a best management practices approach to handling stormwater, which is a tactical approach where we concatenate tactics, which often don't work. But we tend to take the same BMPs all over at every project. Well, in many parts of Germany, they'll say for every cubic meter of water that runs off your property, you owe us 3 Deutschmarks per annum forever. That has led to unbelievable creativity in architecture, landscape architecture, and parking lots, and all these things, so that a lot of German landscapes that are made do not have any runoff. And what that does, what I prefer personally to that way, is more of Americanized freedom to be creative and the incentive to be creative than what we have, which is more of a tactical, dictatorial approach. And so if we would, I think, readjust our performance metrics, say, and develop regulations around performance metrics rather than best management practices, I think we could revolutionize the whole wetland and mitigation industry.
Right.
and mitigation approaching. But as long as we stay with the BMP approach or the treatment train, we're not going to get there.
Right. I when I was on your website, I blundered into a link for another website. I don't know, I think it was maybe, I don't know what university hosted it, but it was a place where you could enter your floristic quality data and generate this. So it's a big database.
Yeah.
Is anybody synthesizing anything out of that database and patterns or?
Well, you can sign up and start putting your own data in. There are a lot of databases around the country.
Right.
And you can, that's a free, what they call online FQA Calculator.
Right.
And that was done right up here in North Branch. The local people who were trying to make this available to people. And that you can do, I believe, transects and inventories in that.
Well, but my question is more of, it's great to have data, great to get it an automated C rating, but is anybody trying to piece any story together with that, like across different kinds of habitats or conditions, or is that just for now just a building up of a database?
Well, it's right now it's just a tool that people are using. I don't think people are trying to synthesize it and look for the sort of broader forensic analyses, which would be an interesting thing to do. I think you first have to define your question, and then look for ways of solving the question, and rather than go the other way and look at data and try to develop a question. And so, but I do think that would be something worth exploring.
Well, I see. Yeah, there could be very interesting patterns, and by community types. Don't know what those might be, but when I looked at that, I thought of that.
Well, you can look at, for example, all those areas and all the states that have mean Cs in the 4s, and those would be the unmitigable areas.
Right.
Those would be the irreplaceable areas, and you can start to salt those out, and then look at areas that are also doing restorations and seeing how well they're doing.
Right. Right.
If they're doing, if they have serious monitoring going on.
So in like a bigger picture discussion, thought while you were talking that hit me was, okay, so you have this influx of water, rain, into these soils. You have evaporation, but you had this movement of water that was regulated in temperature and chemistry, subsurface, and then you have these wetlands. And I was thinking about, are there patterns, floristic patterns of distribution and species associated with this ecology, this hydrologic ecology of how this water's moving, post-glacial patterns? I guess one would be fens.
And those fen species all have mean Cs that are well above 5, most of them.
Okay.
And so you could probably go through and pull out all those things that were FAC or wetter, and look at the C values. And well, I show you. No, in this book here, you've probably seen this. That
this is the original.
Here you see. So here are the weeds.
Right.
You see. Then here's the distribution of wetland plants, upland plants, and so it's pretty normal. What we've basically done is we have eliminated this part. And so now we pretty much eliminated most of our remnant native wetlands, except for those that have been preserved.
Right.
Not only the wetland preserved, but the upland preserved around it.
Interesting when you point that out. Like if you go to the southeast United States, the flora, literally not every spot you go to, but generally the flora is rated as facultative.
Oh, well, in the sand. Okay, so where you have sand, we have that here too. And sand is a harder thing to develop because if your water table is actually, you can get some pretty good vapor pressure even in gravel. So people play what they call gravel gardens,
Right.
and you can get pretty good growth in a gravel garden. And so in sand, coming up with even with C values is a little trickier because sand is more forgiving that way.
Yeah.
And okay, so most of the weeds, the common weeds, we have over 1,000 weeds, but there are about 120 really common ones. Most of those have their origin in the Fertile Crescent and started following agricultural people around the world. They were used to the arable soils. That's where their evolution was. And so when you get into the sandy district, particularly the wetter sands or the sands and gravels, you don't have the weed competition.
I've never heard anybody discuss why is it all facultative. So that's very good.
Well, because the ecotone with sand, particularly in the flats, like in the outwash flats, overwash flats of Florida and whatnot in South Carolina and whatnot, that is a really, you can have, things that you think are obligate plants growing what looks like just sandy dune, but just a little ways down, you've got water.
Yeah.
You can see that up at Illinois Beach here in the sand, where Portentilla fruticosa looks like it's growing on a sand dune, it's actually its feet are wet.
Right.
And so somebody who declares it upland because the soil looks upland, actually, anyway, it just gets a little bit befuddled.
You're right, yeah. No,
but to see facultative is, remember, at the end of the day, there really is no such thing as a wetland.
No.
Or an upland.
Right.
It's all just the same amount of rain falls everywhere.
Yeah.
And so it's just how each place where it falls deals with it.
That's right.
But the whole Wetland Act, the whole was born out of the Fish and Wildlife interest in ducks and in fish,
Right.
which were clearly wet land.
Yes.
And the lobby that came to produce law that were duck hunters and fishermen. And so the whole orientation to the idea of a wetland, and in fact, when I was at the Waterways Experiment Station a number of years ago, they asked me to come up with what they call the wetland plants of the Midwest. And there wasn't a lot to draw from at that time. This is in the early 70s, because the people who talked about wetlands were Fish and Wildlife Service, and that was the orientation.
Right.
And so now we've, in the application of Section 404, beginning in the 80s, we did the best we could, but there's obviously the way the whole, since we're back to 87 manual, well, the way that works is you have to get to the edge where you're prevailingly fackle up rather than fack wet. But in the Midwest, that can be a very broad zone. I will tell you this though, where the system has, and I've published about this in one of the papers on it. It's called. I had something called. I published something about the comments on the 1991 proposed revisions to the 1989 manual, and in there I went after this idea that by including weeds in your transects, you obfuscated the relationship between plants and soil. So it sometimes seemed as that you were getting a wet soil but upland plants, and that's because weeds are not that calibrated to soil wetness. They're calibrated to soil disturbance.
Right.
And so what you do, if you give each wetland category, say numbers like we did, negative numbers to wetland plants and positive numbers to uplands, so you have scalar values from -5 to +5. If you just take a transect and looked at the mean wetness value, as you go in that transect out of the wetland where it's obvious as wet, to the edge, about the point where you get out of a hydric soil is where you get out of wetland, where you get into the upland plants. It's a much more robust correlation between soil if you use wetness coefficients and relate those to the soil.
Right.
And so the weed as it were, the allochthonous element in the system have obfuscated a lot of what we're seeing.
Yeah.
And
Yes.
so a lot of places it's very difficult to correlate soil with the
Yeah,
plants.
but if you dropped in many places, if you dropped out the weedy component,
You wouldn't have anything.
you wouldn't have any.
No,
You wouldn't
that's
have any
true.
plants to record.
No.
That was a question earlier when you were talking about prairies and burning every year. I kind of wanted to ask, how does burning? What is the physical, chemical reaction? What is that burning? When you burn, get a response, and you say burning every year is better than every 3 years, generally speaking. So, what is burning doing that it causes such a positive response?
It's doing a lot of things, but what it's mainly doing, it's been part of the system for thousands of years.
Right.
Ever since the glaciers left here around 15,000 years ago, and the Indians started moving in, particularly by the time by the hypsothermal, the Indians were pretty much managing the land. And so the landscape, all these native plants co-evolved with fire and Indians, and they burned the land every year.
Okay.
And so what physically happens, as I mentioned already, when you burn and you have bunch grasses that do not have lying down matted material, you have all that dew can come down through and into the ground.
Right.
Because those leaves are pulling up average daily temperature water.
Mm-hmm.
So that dew comes on them and comes right down. Actually, there was a study down in Mississippi I think it was in the middle 40s, where they covered a crop of plants with a tarp and didn't let the dew in at the night. Their production dropped 40%.
Wow.
So the night dew is very important in a healthy system.
Mm-hmm.
The other advantage is when you don't burn, the prairie gets started later, okay, and it's got to come up through all that duff, and so you lose. If you think of every grass blade as a photovoltaic panel, then the more square centimeters of photovoltaic panel you have converting sunlight into phosphoglyceraldehyde, eventually into root mass, the healthier your root mass. So not burning the prairie can be the equivalent of light or even moderate grazing, particularly out west, because you're removing solar panels.
Right.
So you've lost the ability for the system to produce organic matter below the ground. Another aspect of that is when you don't burn and you start losing organic matter, particularly in sand, the soil can become more leachable, and so the nutrients that C. Hopkins cafe, if you will, that must be standing up in the soil where plants are every year needing it, will leach away.
Right.
And so it's important to have a strong, healthy soil organic matter. The other thing is, what that burning does is it brings out all the flowers that are there. So many of our native plants that flower cannot come up through all that duff, and just will not happen if there's no burn.
Okay.
And so, all of those flowers need pollinators.
Right.
And all of the pollinators and bees and insects need flowers. So when you don't burn, let's say for 2 or 3 years, or even longer, when you get a fire, so when you're burning every year, the fire is a scudder. It kind of just scuds across, or explodes across. The heat going up, I've seen 30-foot flames go over frost and not melt it, because the heat's going up.
Okay.
And so when you don't burn and let it go for a couple of years, then you burn, you've got a parboiler.
Mm-hmm.
Okay, and so you're cooking now.
Right.
And this makes it hard on the insects for a number of reasons. It's a more complete burn, not a scudding burn. So all the standing insects that oviposit in combs and whatnot make it harder on them. Plus, you don't have the flowers next year, so you damage the insect population when you burn every third year or fourth or whatever, and it can take 3 years to recover because the flowers aren't there, and so the population is hit and they don't have any flowers. But if you burn every year, you have all the flowers and a strong population. Mm-hmm. So if some do die, it's not a big deal.
Right.
And so what Laura has found, my co-author, is that in these annually burned systems, that's where she is every day, botanizing in systems that are burned every year, because she's working on the insects, particularly the bees, and they need they need the flowers.
Right.
And you can't have bees without flowers. You can't have, most of our wasps need flowers. Most of our murids need flowers or plants. And so these plants, their populations suffer when you don't burn. So there's, plus, the native people have to remember that the people who lived here prior to contact had to have all resources within walking distance. So all of the medicine plants, the spirit plants, the food plants, the fiber plants had to be produced every year in abundance within walking distance. If they would have had some young chief's son who grew up and went off to Yale and studied to become an ecologist and got a PhD, and it came back and said, "Dad, we shouldn't be burning this much." He says, "Son, you I don't know where you're getting that idea." But they knew what they had to do. They would perish. Right. And so that was then. So the human cultural relationship with the landscape was as much a part of the system as the abiotic aspect. And the biotic aspect, it's the cultural aspect. And this is often forgotten when we're doing restoration, is that we have to also re-engage the Aboriginal culture with that if the plants are to do well.
Right.
And so the burning is probably doing a lot of things, and it's even different in the woods. So but somewhat similar. The point is, you can go on and on about sort of Cartesian reasons why what it does when it burns, but the main thing really is that was the way it evolved.
Okay. Yeah. Well, it was certainly managed that way for thousands of years.
And before that, there was ice.
True. Yes. Which made me think. Earlier in a discussion, you mentioned like the eastern deciduous forests and the closing in of the canopies, all due to lack of burning, and what that does to the soils. But in the west, you don't have that same kind of a canopy cover, and the understories, you don't have the same sort of shrubby growing in sort of understory of the east.
Well, what you do, you sort of do, because there was a picture taken of Yosemite in 1860, and you could count the lodgepole trees in the valley of the Yosemite from that picture. You go back to the same promontory and take the picture again as it was done, like in 1960, you can't see the valley for the lodgepole. And so the lodgepole is doing two things. It's closing in with shade and dropping needles like there's no tomorrow.
Right.
So you snuff out a lot of that landscape that once had sedges and grasses that provide organic matter and healthy soil. And so now when you get a burn, it's a crown fire, right, and it's a cooker. And you've lost the soil. So when it rains, it just flows across there. And so when the Indians of California have been telling the white people this for over 100 years, you've got to burn in the coastal ranges and the Sierras, otherwise it's not going to work. And so where like in the oak timbers of the coastal ranges, for example, in Northern California, for example, those oak leaves, if you don't burn, a lot of those native sedges and grasses languish. And a lot of it's been grazed out, and all you got is cheatgrass,
right,
of some kind, or some kind of oats, and the soil's gone. So now when it rains in California, the water, what used to have base flow streams, this is the way we did here. The streams just keep flowing out of the mountains because the water going in and working to the streams. A lot of the discharged wetlands. Now the water flows off the surface or soaks the silts, and you get mudslides. And you get wildfires. They wait until the Santa Anas are there, and then they let it catch fire, or something catches it fire. If they burned every year, they wouldn't have to worry about it. Right. But so the same is the problem. We turned the hydrology upside down in California.
Yeah.
Completely upside down.
Multiple times we've mentioned, at one point, quote unquote, we had a complete native flora.
Yeah.
We no longer have a complete native flora,
right,
and part of your conservative values measures that. And I think once I read maybe in the earlier version of this, 55 or 60% of the Chicagoland flora was non-native.
No, it's right now it's 40%.
40%?
Not native, and we have about 3,149 in that book, although we've added some since that book went to press, but about 40% is not native, and we have about 60% native. But that 60%, or the conservative element of it, is confined to less than 0.5% of the total land area. And so most of the land area of Illinois has either corn and bean on it. That's a disaster environmentally, because we're not putting organic matter back in, and or it's rooftop or pavement or drug-dependent rug, the lawn.
Right, drug-dependent rug.
Well, that's what it is.
Yeah.
It wouldn't last a growing season if you didn't keep it mowed and pour out the drugs.
Right.
And and then the lollipop trees and the poodle shrubs.
Yeah.
That's what our infrastructure aesthetic thinks is nice.
Yeah, right. Well, you have that same degradation, but like in New England, the forest, there's weedy stuff everywhere, but it seems a lot cleaner, quote unquote, less invasive or non-native content. It's not by any means pure, but if it's 40 here, I would have to think it's 25% there. It drops.
Well, you should look at some eastern flora and find out what the percentage is. Yeah. Look at what's his name, New England flora, and see what the percentage of weeds is.
Right. And even in Alaska, if you get way back in, you still find non-native species.
Yeah.
I'm not sure how they get there besides wind ducks or birds.
Yeah.
But it's amazing.
They get around.
Yeah.
We've been everywhere. I mean, we've been most places and track it in. As you move north, they get rarer because everything gets rarer. But the east is difficult. Here in the Chicago area, we didn't become a state until Illinois became a state in 1818. Chicago didn't become inhabited by Europeans until 1832. So we're very close to it. In New England, it was 200 years before that.
Right.
And it was so the trauma and the obvious change we've already missed, because ecology wasn't born until 1899. Actually born right here in Chicago to a large extent with the Henry Chandler Coles and the successional thing, but it was born right in the period culturally of the Hudson River School of Art, where painters were painting the forest's primeval.
Yes.
The virgin forest. The virgin meaning, in the John Murian sense, of the wilderness where no man enters. Because if a man enters, it's no longer virgin. Mm-hmm. And so the idea that we have virgin forests out east, but not here, you see, or people try to call some of a virgin forest for our forest out here, but it literally meant it's a nonsensical idea. But that was since all the Indians of the east had been long gone by 1899, and had this succession going on. We felt that was the paradigm that was normal, and so ecology as a science and its first principles were born in the era of the Hudson River School of Art, and the idea of succession became part of that. That human beings were involved, so it must be something internal that kept these systems virgin and healthy, but not man. And in fact, us '60s kids, when we read Rachel Carson's book, and we learned that we need to be a little bit more circumspect about our dispersion of chemicals and whatnot, we drew back. And also, as children of John Muir, we wanted to stay out of the wilderness. And so it took many decades to rediscover that the Indians were people too. And the human beings of Massachusetts or Chicago or Lake County, California, were human beings living here, and they've been living here for thousands of years. And so they weren't virgin in the sense that man had not entered.
And man had not managed.
And man had not, that's right. And so they were managing the land intensely. In fact, Kat Anderson wrote a book entitled Before the Wilderness with Blanchard. And in there she talked about how the landscape of Lake County, California in particular, was managed. There was one of the chapters in there, managed intensely by the grandmothers and the grandfathers, and how they managed the land. In fact, she got in with some of the grandmothers. She was an ethnobotanist, and discovered after about 3 years she had enough confidence in her to teach her that so many California plants were dying in the national parks and state parks, not because the white man was building kiosks and gas stations and motels in these places, but because the white man thought the grandmother was not natural and took her away from the harvesting places. Mm-hmm. And so that's when so many plants began to die, because grandmothers were removed. And so many native plants also need to be harvested. And in fact, burning is important in the East, for you sure. Like I say, Massachusetts, Plymouth was burning on an annual basis by the native people, and it wasn't discovered until a number of years later that they needed to start doing something too, because they were losing their cattle forage. A Dutchman, sea captain, went up the Hudson in 1650 and described both sides of the Hudson as nearly treeless because of the habit of the Indians to burn off the brush every year. Oh. But I'll tell you also something, that I was at near Burlington, Canada, with a friend of mine, a Canadian ecologist, Merrick Sharp, or North-South Environmental, very good biologist. But anyway, there where the Niagara Escarpment comes out above Burlington, it was stepping down, and there was older oaks in there, and then young maples and lindens that were coming up, and it looked to me like what I would call an unburned timber that needed a fire, but I didn't think would carry one. I said, Merrick, what's going on here? This can't burn, and yet it's getting too thick. He said, well, you have to remember, Jerry, that from time beyond mind, there'd been a great Haudenosaunee village up here, removing enough wood for cooking and heating and building things, but never so much wood that there wasn't always wood, but enough wood to remove it and keep enough light in for the women's plants. So trying to back calculate how many BTUs it would take to keep a tribe of Haudenosaunee or a band alive on a great bluff top year after year in a Canadian winter. And so the calculus of harvesting the woods, even I was doing some work with the Potawatomi Indians over here in southwest Michigan, and calculated that even if we thinned the woods to where it needed to be and started burning every year, there'd be enough new growth of wood every year that they'd have to remove about, I think I calculated about a cord per acre per year harvesting in addition to the burning. And so that was a very intense, very sophisticated calculus these people had with their land.
I just had this thought of, if you think of DNA and complexity of genetics and influences on species, the interaction between man and the landscape and the vegetation is as complex, is a complete different complex story. After the DNA's done its thing, then you throw this whole human interaction in to the what we thought was virgin landscapes.
But see, that's the doctrine,
right?
Just the way at 1818 the doctrine of water was collect, convey, and discharge it away. And with the Clean Water Act, we said, let's collect, convey, and discharge away, but less badly with BMPs. What we need to do is say, let's receive every drop of rain as a blessing and a resource, and change the doctrine. But until we change that doctrine, we're going to be asking questions and answering them in the wrong doctrine. And so it's the same way the ecology started asking and answering questions in a doctrine of succession and virgin, rather than a doctrine of a human cultural relationship, but with the people had to manage it for optimum biodiversity, otherwise they would perish. And so they had that little transfer RNA coming in all the time saying, you mess this up, you're going to die.
Jerry, I would like to thank you for not only your discussion of the seed values of conservation, floristic quality, but also your in-depth descriptions of soil, relationships, water quality, much more comprehensive look than plants out of place, but plants are part of the environment. So I really like to thank you for your time
you're
for
welcome.
this
It's been a
today.
pleasure. After a number of years, I've always enjoyed working with you, Bob, over the years. You know, it's trying to find a way.
Yeah, it's always, as a botanist,
Yeah.
we're always trying to find a way.
Right, yeah.
Okay, well, thank you very much
You're
then.
welcome. Yeah.